So now we're going to go on to which data set has more variability. We've covered the mean. We also briefly talked about the mode and the median, which are the measures of central tendency. Standard deviation is the biggie in terms of variation, okay, or dispersion in the data. Now, so what I want you to look at here is just which data set has more variability naturally. So if you look at the top set, which has 9 data points, there's basically no variability. It's all the same. All 3, the average is 3, the mode is 3, the median is 3. This, on the other hand, has more variability. So it shows you that it's important to consider how dispersed the data is, or are, excuse me. So in this case, 0 variability, no standard deviation, and in this case, there will be a standard deviation, which represents, on average, how far things fall away from the mean, in which actually this is, if I remember correctly, 3. So this could be a survey item. I am satisfied with my coaching experience on a scale of 1 to 5, with 1 strongly agree and 7 strongly disagree. Okay, so let me see where we go to next. I don't know why it does this. Let's go to the next. Okay, so standard deviation, again, is the other biggie in descriptive statistics, and it reads as, in papers, S period D period. It's a measure of variation around the mean of a set of data. And again, taken together, the mean and the standard deviation represent the lion's share of descriptive statistics reporting in research. The other key measures of variation are range and variance. Now, what I'll show you is, though, variance is captured in it's captured in the standard deviation measure. So what you really have to think about is range beyond that, which is the difference between the smallest point of data and the largest point of data. Okay, let me step out of this. I'm going to show you briefly how to address standard deviation calculations. So this is what you just saw in the last screen, which was, or the last slide. Remember, this is all the 3s. So the 3s here, so don't focus on this right now. Focus on this one. And so if you add all of these up and divide them by 9, you get 3, which is the mean. And let me see if I put in here. No, I didn't even do it here. This is how you would calculate that. Equals average, parenthesis, A18, which is that particular cell, and the colon means to sum with A or through A27, 3. That is your mean. Now, if you then look at this column heading, actually also, let me relate it here. Okay. I'll make it easier for us here. Okay. Okay, so we get a little more space. Now, here is how you calculate. My phone is ringing. Okay, back. So now if you look at it, it's called consider the data point versus the mean. So what you would do here is subtract each data point from the mean. So in this case, this data point minus the mean is 0. There's no variability away from the mean. Again, second data point. 3 minus 3 is 0. There's no variation from it. Now, then, and again, this is how you're calculating standard deviation. So what you would do is you square the difference. So multiply it times itself. In this case, 0 times 0 is 0. And then you would add these up to get, here, put this down here, to get 0. That would be, in this case, the sum of squares. But what you need to notice as I'm going through this is you're trying to figure out how far away each data point is from the mean, because again, the goal is to understand variability in data. So once you have the sum of the squares I'll show you in a minute, you don't have a standard deviation. It's going to be 0. So there's no range because it's all the same data, all the same. Every single data point equals the mean, so there's no standard deviation. On the other hand, the one that I just showed you above with the one with the variability, if you average this to get your mean, if you notice here's your formula, equals average A3 through A11 equals the mean. Now then, if you subtract each data point from the mean, and you would do absolute value in this case, so there are no negative numbers. So 1 minus 3 with absolute value is 2. 5 minus 3, 2. 1 minus 3, 2. 5 minus 3, 2. 2 minus 3 is 1, and so forth. Then you square them. So 2 times 2 equals 4. 2 times 2 equals 4. 1 times 1 equals 1. 0 times 0 equals 0. You add them up to get what's called the sum of the squares, and then you subtract, oh, how did I do this? So you subtract 1 from 9. And again, I don't expect you necessarily to know how to do this. I just want you to get an intuitive sense of how this all works. So you basically divide the sum of the squares divided by 1 minus the number of data values. In this case, there were 9 data values. You take off 1, which equals 8. So you divide 26 divided by 8, right here, and that is your sample variance. So remember, I told you that variance is another number that represents the variation or dispersion in data. But notice that all you do then is take the square root of the sample variance to give you your standard deviation. And notice here's the calculation if you ever wanted to do it in Excel. Okay, so you would take the square root of the sample variance to give you your standard deviation, equals SQRT, and then the cell number, C14, in parentheses. And you'll notice that the range is 1 to 5, 1 all the way up to 5 as a high point. So then let me help you with one other one. Remember, there was a question on your homework in which I posed an additional attribute that could have been considered in Dawson-Long called action research. So let me show you. Again, here are the Dawson-Long attributes, if you remember, on what makes them interesting. So I thought, let's add one called employs action research. Now, the reality is that if that were asked, nobody would consider it important because it's just one paradigm. And as I told you, action research is still gaining clout or legitimacy. So what I pretended is that we have 20 response rates on the action research paradigm, as though the same people who responded to the Dawson-Long article responded on the action research into attribute. Now notice 1, 1, 1, 1, 1, 1, 1, 1, 1, 2 people considered it a 2, which would have been, in this case, somewhat important. Okay, so that would have been a 2. A 1 would be unimportant. And obviously, there would be more respondents in the Dawson-Long article, but nonetheless, this serves our point. So the mean would be a 1.1. And notice again, the Excel calculation is equals average, parenthesis, A1 through colon A20 equals 1.1 is the mean. And let's just for ease of it say, and I'll show you the calculation in a minute, standard deviation, STDEV, equals A1 through A20. So it's 0.3077, and pretty much everybody got that right, so kudos to you. So if you look at this, 1.1 would be the mean. Now let's compare it to everybody else. Whoa. The lowest one is a 1.9. So this would be far below in terms of the mean everybody else. So what we could conclude on the basis of just looking at the mean alone would be this would be totally pretty much unimportant, and would be, we could be confident in the integrity of this conclusion because the variation, in this case, the standard deviation, is low. There's not very much of a standard deviation here because pretty much everybody labeled it as a 1. Only 2 people out of 20 gave it any kind of variation or dispersion in the data, and it was not that much. So we could be confident in this if we did statistical analysis, just using these 2 statistics. Frankly, I find it very cool, and I hope you do too. Okay. Oh, yes, I have to go back there one more time. And so back to our standard deviation calculations. This would be the action research one I just showed you. You should copy and paste this again. So if we want to do the calculation one more time on the action research attribute, we would have, here's the data point. The average is whatever it's going to be, 1.1. If we took each data point versus the mean, which would be, so the mean we'll say is 1.1, or, excuse me, let me see. Let's say it's 1. That's how I did it in this case. It is a little bit higher than that, but let's say for the sake of it, it's 1, right? So in this case, because the standard deviation is very little, I'm simplifying it. So if this were the mean, 1 minus 1 is 0. There's no variation away from the mean on that data point. 1 minus 1, 1 minus 1, all the way down to the 2's. So there's no dispersion away from the mean until you get to the 2. So this signals to you, just by looking at the data, not a lot of variation, not a big standard deviation. When you get to a 2, you subtract 2 minus 1 to give you 1, and 2 minus 1 to give you 1. The square of both of those is 1. 1 times 1 is 1. You add them up, you would get the variance, which is, in this case, I should have done that differently. I think I had 20 data points there. So it would be the sum of the squares divided by, excuse me, I did that wrong. 19 data points. So 1 minus, I think this is 20 in here, or close to it. We'll say it is. And then you get your standard deviation measure by square rooting that. I hope that made sense. Let me see how many data points we have. 1, 2, 3, 7, 8, 9, 10, 11, 12, 13, 14. So we had 17 data points. So in this case, we'll do, because there were 17, you do divided by 16. Okay? So, and then the standard deviation is the square root of the variance. And the range in this case is 1 to 2. So again, these numbers are a little bit different than what I just showed you for the purpose of simplicity, but the idea is there's not very little standard deviation. So what that could tell us is we could have a lot of confidence now in that particular number. Now, if we look, the widest variation is something like emphasizes practical applications. So some people rated this quite more important, some people less. And so there's more variation in this data than, say, well, the lowest was investigates totally new questions or novel topics, which gave it more integrity because there wasn't a lot of variation. So this has slightly less integrity as an attribute in terms of knowing that it's important to being interesting research than would be, say, this, for example.